So hi, and welcome back to another Æther Physics. Today we're working on the physical lines of force of Clerck Maxwell. In last episode we talked about proposition 1 made by Clerck Maxwell, and today we're going to continue in this mechanical lines of force, or what is it? The theory of the molecular vortices applied to the magnetic phenomena, and we're continuing in proposition number 2. Last video we ended up with the formula P1 minus P2 is equal to 1 divided by 4 pi times mu times the velocity squared. And we were talking about a vortex which has a center of P0, an edge P1, and somewhere parallel to P0 we can have, for instance, P2, so this line could represent P2. We can even have another vortex here and call this P2. But yeah, it's about the pressure due to motion. The actual stress may be resolved into a simple hydrostatic pressure P1 acting in all directions and a simple tension P1 minus P2, or 1 over 4 pi mu v squared acting along the axis of stress. P1 can be a hydrostatic pressure in all directions. P1 minus P2 would be a tension. Okay, so we're here at stresses. We can call Pxx, Pyy, and Pzz. We can call this the normal stresses parallel to the free axis. In another video we talked about for instance, a cube, and in this cube we can grab a surface, for instance the front surface and the back surface, and if we call the three dimensions, we call, as usual, this we call x, we can call this y, and this z. So Pzz, it will be a stress over the zz direction. For instance, I grab red, Pzz, circle of red will be pressure between the front and the square here in the back, surface in the back. So it's between two surfaces, two sides of the cube, of the portion of the fluid. Same idea, the y here, for instance, we call this the y direction. Y is about the top plane here and the bottom plane here, and it's the stress between the top part and the bottom part. And same idea for the x direction, and the x direction would be both sides, this square here and that square over there. So you see that we can talk about a portion of the fluid and use stresses in terms of effects on the fluid. So x stress, y stress, and z stress on a portion of the fluid. Yeah, we can call Pxx, Pyy, Pzz the normal stresses parallel to the free axis xyz. Considered positive when they tend to increase those axes, and negative if they decrease. And if Pyz, Pzx, and Pxy be the tangential stresses in the free coordinate plates. So if we have P, what did I say? I need to write it down. Y, Z, P, Z, and X, and P, what am I missing? Y and X, I guess? X and Y. These would be tangential forces. Tangential. I really don't like that word tangential, but what these forces mean is a rotary force. So Pyz would be YZ, would be a rotation over the x-axis. As you can see, there is no x here, so that's the clue of telling us that it's a pressure in a linear direction y and a linear direction z, which is a surface. And it says y and z, so we see here we have a y. Y will be this line here, this green line would give us the y, and this part would give us the z. So Pyz would be a rotation of the surface. It's the same as, or not the same, but we can also say Pzy. And then we're talking about the other square, other side, other part of the cube. Also green. And the same idea is for the pressure over x and z, and here the pressure over y and x. Blue. As you can see, z and x, it has no y in it, so it is on the y direction, talking about the plane in the z and x direction. So it's the top plane and the bottom plane. And eventually, same for these two, x and y and x, which is in the z direction, the depth, and that will be front plane and the back plane. And these are rotary forces, or they call it the tangential stresses in the three coordinate planes. Considered positive when they tend to increase simultaneously the symbol subscribed. Then by the resolution of the stresses, we can write down that Pxx is equal to 1 over 4 pi times mu times v squared times the dimension L squared minus the hydrostatic pressure 1. Same idea for the other parts. 1, 4 pi mu v squared L m in this dimension squared minus p1, and over the z direction will be 1 4 pi mu v squared Lm n squared minus p1. And as I said, p1 is a hydrostatic pressure in all directions. And L, M, and N again are the directional cosines of the axes of the vortices with respect to the axes x, y, and z. Here it gets a little bit harder again, or maybe this makes it easier even for us. BYZ, PZY, they have again 1/4 pi over mu over v squared. As you can see, the beginning of this formula is all this formula here. The extra part is this. It's a little bit different. So again, here the same. And this is not L squared, but this will be the dimension m times n. And here we have 1/4 pi mu v squared. And this is over the n and L dimension. And here we have 1/4 pi mu v squared. And the last one is L and m. It's a rotating force. And of course, this formula, these three formulas are for the first three here, and the last three would have m and n switched, but that doesn't matter because m times n is the same as n times m, or n, l, l, n. It gives the same answer. Here we get into Maxwell's real notations. He says, interesting thing, alpha is v times l, beta is v times m, and gamma is v times n. V times L, alpha, v, L. V times m is here. V times n, here. As you can see, we're talking about all the dimensions that the ether particles can have, the x, y, z dimensions. If we would rewrite these formulas here, we can remove v times L, v times m. The last one, we can just say that this will be alpha squared, beta squared, and gamma squared. ML would be beta gamma. So this is beta gamma, and gamma alpha, and alpha and beta. Oh. Small mistake. So, as you can see, it's getting a little bit more complicated already, but we're gonna make it even more complicated in the next video. So this was about stresses in all directions, all dimensions, directions, non-rotating, rotating part. So these were the first two parts of the physical lines of force. You might have recognized it because it is about what we've talked about before on this channel in previous videos. We were talking about the pressure inside the vortex, and we were talking about stress tensors. You might already figured it out that we've already been over these two ideas before in other videos. Next episode is going to be a very interesting one. It's gonna be a lot harder in physical equations than this video, but yeah, I enjoy making these videos, you know? Yeah, I enjoy just vlogging or doing whatever. I'm just trying to explain to myself what this man actually tried to explain to the entire universe. Or universe, maybe only just our precious planet. Because I think that on other planets they eventually figured out the same idea, but they just call it different. Because I think that here on Earth we haven't figured out whether we call a distance in meters or inches, miles, kilometers or yards or whatever terminology you use to talk about distances. We can just call it a linear dimension. And I think that everywhere in the universe they figured out that there are linear dimensions and velocities, for instance. Even time is an idea that we ourselves created, because who are we to say that between would be 1 second or something. Some of the basic ideas of fluid dynamics in ether physics. I'm really looking forward for the next episode, you know? Because in proposition 3 we're gonna build a hella big formula, and we're gonna make it only using these basic formulas and expanding it in a way that, man, I don't even know who can even imagine this, who can even think of this. So thanks a lot for watching, and see you guys next time.